So in the previous lecture on NMR theory, we discovered that there are three pieces of information you can get from looking at each NMR signal. And the first of those was by looking at the chemical shift, delta, which had units as parts per million, defined as the shift downfield from the internal standard, tetramethylsilane, in hertz, relative to the spectrometer frequency in megahertz, such that for our instrument with a 7 Tesla magnet, seeing proton at 300 megahertz, there are 300 hertz in each part per million. And the chemical shift tells you something about the electronic environment surrounding the nuclei. So this will allow you to identify the presence of functional groups. If you see a peak in the aldehyde region between 9 and 10 parts per million, you can start looking for an aldehyde. If you see peaks between 7 and 8 parts per million, you can start looking for the presence of an aromatic compound. Peaks between 3.5 and 4.5 parts per million, you can start looking for the presence of an alcohol or an ether, hydrogens adjacent to that O, or chlorine maybe. So we explained why most nuclei are shielded relative to the applied, or shielded from the applied field. So if we have our H0, our applied field, and we have our nucleus, say our proton nucleus, we explained that there would be electron circulation going around the nucleus in response to the applied magnetic field. And that electron circulation is going to cause a current, or is going to create a current, which will then in turn create its own magnetic field. Because moving current always creates its own magnetic field. These magnetic lines of force would look similar to what you would get if you placed a bar magnet under a piece of paper and shook iron filings on it. So we've got this induced field, and in here where the nucleus is, that induced field opposes the applied field. So that when we do a vector sum, our effective magnetic field, the field actually felt by the nucleus, is less than the applied field. This causes shielding. The more electron circulation, the stronger the current, the bigger the magnetic lines of force, and you'll have a larger induced field. So putting an electronegative element and pulling some of that electron circulation away causes it to be less shielded than it would be in the absence of the electronegative element, and causes these peaks to be shifted less, or to be deshielded, shifted further downfield, shielded less. So that explains the presence of the electronegative element, but it doesn't explain why alkenes show up even further downfield, between 5 and 6 parts per million, even though there are no electronegative elements, and aromatic compounds go still further downfield, usually between 7 and 8 parts per million, nor does it explain why alkynes behave quite differently from the other carbon-carbon pi bonds and have delta in the 2.5 ppm range-ish. So we've got compounds with pi bonds behaving very differently than ordinary hydrocarbons that just have single bonds. So what is it about the pi bonds that cause this very different effect? There must be something. And the key to understanding the effect of the pi bonds is to understand the way the molecule orients itself relative to the applied field. An alkene, and same is true for aromatic compounds, will arrange itself perpendicular. The orientation of the carbon-carbon pi bond orients perpendicular to the applied field. This is an upside down T. Is the mathematical symbol for perpendicular. So we've got that molecule lined up perpendicular so that only these two carbons are in the plane of board. We've got two hydrogens out, two hydrogens back. It's lined up like this, flat. The pi electrons, because the pi bonds are both above and below the plane, are going to circulate. And that pi electron circulation is going to cause a current that once again causes magnetic lines of force to be created that in the center of the circulation create an induced field that opposes the applied field. The difference is that in the center of the circulation, in the center of the pi bond, there aren't actually any nuclei. The nuclei are out here. And where the nuclei are, the induced field actually reinforces the applied field. So when we make a vector sum, we're going to find that the effective magnetic field felt by the nuclei, which are out here, is larger than the applied field. These hydrogens here, these protons, are truly de-shielded. They are less shielded. They feel a larger magnetic field than the applied field. When you have an electronegative element, all you're doing is reducing the amount of shielding. Everybody is still shielded, but they're not as shielded. Here, they're truly de-shielded. There are two electrons in an alkene, in an aromatic compound, which orients itself the same way. And so we would have our same H0. But now we have our aromatic compound, benzene, for example. And again, it's going to align itself perpendicular to the applied field. So that only the hydrogens in the 1 and 4 position in their respective carbons are actually in the plane of Bohr. And we've got these two carbons and hydrogens out, and so it's flat again. We're going to have a similar circulation above and below to what we had before. But now those 6 pi electrons are circulating, and they're circulating all the way around the ring, interacting with all 6 nuclei. Where this was just 2 pi electrons circulating, now we have 6 pi electrons circulating. And we refer to that as a ring current. It's creating a current. As before, that current is going to result in its own magnetic lines of force. And in the center of that circulation, magnetic lines of force are such that the induced field opposes the applied field. But out here where the hydrogens are, that induced field reinforces the magnetic field. And it's larger. This induced field is bigger than the induced field for just 2 pi electrons. So we should expect to see a larger effective magnetic field. And that effective magnetic field is going to be significantly greater than H naught. So it makes sense that 6 pi electrons circulating in a ring would cause a greater induced field and a greater amount of de-shielding relative to 2. Why is it that alkynes, which have 4 pi electrons, aren't in the middle between 6 and 7? That's what you might expect if it just correlated with the number of pi electrons in the system. So there must be something else going on with the alkyne that's causing it to be quite a bit upfield relative to the other carbon-carbon pi bonds. And the key is in the way it orients itself relative to the applied field. Both the alkene and the aromatic compound oriented themselves perpendicular to the applied field. The alkyne is different because the alkyne has two pi bonds. It has pi Y above and below the carbon-carbon pi bond, but then it also has pi Z. And pi Z is out in front and also behind. So if I look down the carbon-carbon bond in a Newton projection, I've got a pi bond that's above and below, and I've also got a pi bond that's in front and behind. As a result, electrons can move from one pi orbital to the other pi orbital, those are degenerate, and we can actually get electron circulation not above and below the carbon-carbon bond, but around the carbon-carbon bond. That causes the alkyne to orient itself not perpendicular to the applied field, but parallel to the applied field. And that little double line is the mathematical symbol for parallel. The electron circulation then is going around the bond, kind of like this, going around that pi bond, creating the current that results in these magnetic lines of force and induced magnetic field. And out here, that induced magnetic field reinforces H naught, but the nucleus isn't out there. The nucleus is now here. And where the nucleus is in the center of the ring curve, which creates an induced field that actually opposes H naught. So H effective, in this case, is less than H naught. So instead of shifting down to 5 and 6, which is where you would expect it to be if it was just a single carbon-carbon bond in an alkene, it kind of shifts it down, but then this pi electron circulation here causes a upfield shift relative to where it would be in an ordinary alkene or an aromatic compound. So they're still downfield relative to an alkane because of the presence of the pi bond, but they're not as far downfield as the CC double bonds, because instead of orienting themselves perpendicular to the applied field, they orient themselves parallel to the applied field. And that puts the hydrogen in the center of the circulation of electrons rather than on the outside edge of the circulation of electrons, and completely changes the direction of the magnetic field vector that's caused as a result of the electron circulation. There's reinforcement for this idea of a ring current from larger aromatic molecules that have more pi electrons. This molecule here, which consists of 4 interlocking benzene rings is called pyrene. It's a polycyclic aromatic hydrocarbon that's found in coal soot and has been implicated in carcinogenic activity. It is possible to reduce the double bond in the middle by adding H2 gas to form dihydropyrene. Which has one hydrogen pointing up and another hydrogen pointing back. There are 7 pi bonds, which means there are 14 pi electrons in this system. And that follows what's called Hoover's rule, which says that if there are 4n plus 2 pi electrons, where n is an integer, in this case 3, then the compound will be aromatic. Because we have an uninterrupted ring of sp2 hybridized carbons, electrons can flow around the ring, and the molecule will orient itself with respect to the applied field perpendicular, the same as a regular benzene ring would. So we've got these hydrogens in the middle here, one of them pointing up, one of them pointing down. Our whole molecule is kind of pancake flat relative to the applied field. And we've got a very strong ring current, because now we have 14 pi electrons contributing to that ring current. That should create really strong induced magnetic fields. So out here, we have a very strong induced magnetic field that's opposing the applied field. So for the white hydrogens, the hydrogens that are on the outside, our effective sum will be much larger than our original applied field. And we're going to see hydrogens that are very heavily shielded. We would expect to see those hydrogens considerably more deshielded than an ordinary benzene ring aromatic. But we also have 2 hydrogens that are in the center, which I've marked in blue here. And in the center, we have a pretty strong induced magnetic field that opposes H0. Which means that the effective magnetic field here is going to be significantly less than H0. And we would expect to see fairly heavily shielded hydrogens. In fact, these hydrogens are so heavily shielded that delta is negative. They've shifted upfield relative to the internal standard, the tetramethylsilane, because this shielding effect is even more powerful than the shielding effect of the electrons being pushed from silicon towards carbon and less hydrogen. So we've got 2 very different chemical shifts. The 2 hydrogens in the center of the ring current feel a much smaller overall magnetic field than the 10 hydrogens that are on the outside. So we might see 10 down in the 9 to 10, or maybe even 10.5, 11 range, and we're going to see 2 hydrogens that are upfield in the negative chemical shift, negative delta. A related molecule that behaves kind of the same way is a 14-member ring without those two central carbons. So we've got 3 Z double bonds, or cis double bonds, and then we've got 4 trans double bonds. And what that creates is 4 hydrogens in the center and 10 hydrogens on the outside. The ring current looks the same as it would be for the dihydropyrene, where we've got a strong 14 electron circulation above and below the molecule, which is oriented perpendicular to the applied field. And then we've got magnetic lines of force that in the center where the 4 blue hydrogens are is causing a large induced field that goes against the applied field. And on the outside where the 10 hydrogens are is causing an induced field that reinforces magnetic field. So what we're seeing here is a delta of -4 ppm for the blue hydrogens in the center, and a delta of 10 parts per million for the 10 hydrogens that are on the outside. Two very different shifts. These are de-shielded strongly, shielded strongly, even more strongly than the internal standard TMS. Okay? And there's something of a competition among kind of geeky chemists to see just how far upfield you can push a hydrogen by figuring out how you can get them right in the center of a very strong ring current. So the evidence for this ring current is that if you can place a hydrogen in the center, you can powerfully de-shield it powerfully shield it relative to your internal standard, whereas the ones on the outside behave the same way as they would for a benzene ring, just more so because we have a larger ring current with a larger number of pi electrons. So other things being equal, the more pi electrons are causing the ring current, the stronger the current, the stronger the magnetic field will be being generated by that, and the more de-shielded things will be, assuming that they are on the outside of the circulation. So the chemical shift can tell us a lot about the electronic environment. It can tell us whether we have an aromatic ring. It can tell us whether we have an alkene. It can tell us if we have the presence or absence of electronegative elements. But it's only one of the pieces of information that we can get from looking at every NMR signal. In the next video, we'll talk about the other two.